All right, so in the last two lectures, we covered properties of light that categorize it like a wave and how we treat it like a wave. We've covered properties of light that treat it like a ray and the properties of that. Now, our last section here is kind of resolves the issue of is light a ray or is light a wave, and we will treat light as a photon. And we'll talk about just a little bit about what a photon is. Some of this gets into some realms within modern physics that get a little bit more complex. So we're just getting a basic survey of what light as a photon means, and we're going to leave it at that. Not too complex, just kind of introducing that concept, and that's really about it. So this will be a very quick lecture, even for me. So, what is the photon model of light? We learned that light is acting as a wave, but we also have these experiments that we see some particle like nature. So there's still, we know light is electromagnetic wave, but it also has particle like nature. It has particle like nature when it reflects and it refracts. So it's got both things going on. So what we have instead is what the theory that was came up was that photons are a particle like component of the electromagnetic wave. So we're saying that there's this what we call a wave particle duality. So both things are going on at the same time. It can have both properties. It can satisfy concepts from both the wave model of everything, right? We talked about different waves, a wave model of everything, and basic particle physics like kinematics. So it can have both things going on at the same time. So here's an example. Here's kind of an experiment. One experiment that indicates the particle-like behavior is a dim photograph. Now we're not talking about like you take a photo and then like lower the lighting, but an actual like photograph on exposed film over time. If or with intensity, more or less waves. If light acted as a wave, if we have less intensity, which is picture one on the right over here, if light acted as a wave, we should be able to see the entire image and it would just be dimmer. But what we actually see, this dim photo number one, doesn't show everything. It doesn't show the complete photo. As we increase the amount of light, increase the presence of light, so we go into photo two, we can see not just that it's getting brighter, but that that the image is becoming fuller. It's starting to form by the time we get to number three a full image, and that is full exposure. So when there's less light, the density of the dots is lower, and we see that it's there. We can see all the kind of the particles that make up the image, but we don't see the full image, and that's kind of it's kind of weird because then, well, how is it satisfying that wave like behavior? So it's a complex thing. Is that the less intense the light is, the less amount of the picture that we see. So that's a great image for this or a concept of this photon model of light. So the photon model of light has three basic postulates that describe what's going on. First, electromagnetic waves consist of discrete massless units called photons. That's very important, especially when you get into relativistic physics, that these are massless. So light doesn't have any mass, but a photon travels in a vacuum at the speed of light. So it's of course 3.0 times 10 to the 8th meters per second. So light travels at the speed of light, and it travels in discrete massless units called photons. So little bundles of energy called photons. All right. Postulate 2. Every photon has a specific amount of energy equal to the energy of that photon is equal to hf. F is the frequency of the wave, and h is the universal constant known as Planck's constant. So you're not going to really have to calculate anything. This is what really gets us into some modern physics, um, in that we get into the what's known as the photoelectric effect, which is actually what Einstein won his Nobel Prize in Science for. That really gets into the concept of light as a photon, and that's how he really settled this debate: light as a wave, light as a particle. So there's some good, quick little videos on there. Feel free to check that out about the photoelectric effect. But there is a specific amount of energy in that photon that's based on the frequency of that wave. So if it's anything in the electromagnetic spectrum, infrared rays, um, ultraviolet rays, all the colors, right? So all of these have discrete wavelengths, which is like for visible light, it's 400 to 750 nanometers. Well, the frequency of that determines how much energy that it has. Okay, and then our last postulate is that if I have enough, the superposition of sufficiently large number of photons, if I have enough photons, then I get the characteristics of electromagnetic waves. Which means that if the more photons, if the amount of photons goes up, then the wave-like behavior characteristics or traits also goes up. So once I have enough photons, that's when I get evidence of the wave-like behavior of light. So it's a combination, like within that wave-like behavior of light, we have all this photon stuff, but if I have enough photons, then I get the wave-like behavior of light. And that's what the complete version of the photon model of light is. It combines some particle concepts, which is essentially 1 and 2, and then it gets this wave concept. If we have enough particles, it acts like a wave. So it's a complex concept, but light is a very complex concept. And when you get into modern physics, you can see that. So that's actually, believe it or not, it's just an introduction into the wave particle duality known as the photon model of light. So by the end of this week, you should have this graphic organizer done, because you should have been filling it out as you do this. And then we're jumping right into the Unit 9 test this week. This is 100% a conceptual test. So you should be able to identify what models of light really are being utilized to verify stuff. So there's a bunch of questions like, what category does this fall under what explanation of light. So very, very, very conceptual test, but no homework to do with the photon model of light, just the test to finish by the end of the week. And we are done covering new content for this school year. So congratulations, there are no more lecture videos that you need to watch. So I will see none of you in the next segment.